So, in this lab, in lab 3, you guys are going to be working with your spectrophotometers, right? In the biochem lab, I'm not in the general chem lab where you guys do your lab. I'm in the biochem lab here, and here we have some research grade spectrophotometers. We have about, let's see, 6 of them here, and there are a couple other ones scattered throughout the department, and they do much of the same thing. The software is more complicated. The machinery in here is more precise and accurate. You have more capabilities. For example, if we take a look inside here, this spectrophotometer has spots for 6 different samples. This cell here moves back and forth. The light comes in right here, goes through a sample, and then is detected over on this side. This specific one also has a temperature control bath. This temperature control bath right here will control the bath, the temperature of liquid. The liquid is pumped through this cell. A coating, kind of a jacket on the outside of this shell, where water goes in and comes out, keeping the temperature the same as the temperature of the water here. So this, you can keep the constant, or the temperature of your sample constant, or change that to temperature. Over here in this one, we have a spot for putting our sample again. And these other ones, these research grade ones, have 2 sample spots. 2 spots to put a sample. And usually what you do is you have 2 blanks, or one is your blank, so you can always measure one beam relative to the other beam. So this here is just a cuvette with water in it. So that is our blank. So I would put that one here, and then I would take one of my samples here. This is an iron solution of iron, salt, and I would be able to then always have a blank there so that we could compare the absorbance of this material versus the absorbance of that chemical there. Alright? In your lab, you just have one spot. This is called a dual beam. In the spectrophotometer in your lab, you just have one spot. Alright? So, again, let's go over here to the board really quick. In your lab, the first thing you're going to do is make yourself a solution, a known concentration, right? A solution of the cobalt chloride, right? So you're making a solution of your cobalt chloride. You're going to know the concentration of that solution. And the first thing you want to do is identify the maximum absorption, the peak. And you do that by monitoring different wavelengths and determining absorption at those different wavelengths. And like it says in the lab, you're going to range somewhere between 400 and 800 nanometers. Nanometers are the units, right, for the wavelength, right? And that means that the wavelength, so this is my, if this is my 400 nanometer electromagnetic energy, or 400 nanometer light, we call it light when it's in this range, right? That our eyes can see. 400 to 700 is generally the range that we talk about our eyes being able to see. 400 nanometers means the wavelength from here to here, so where we start, and we go through, let's see, here to here, right. We went through one whole wavelength. That wavelength there is going to be 400 nanometers in length. Alright? So if it's 800 nanometer wavelength, then it's going to be twice as long. From there to there, that's going to be 800 nanometers. Alright, so that wavelength, that number, is actually the wavelength of the electromagnetic energy. Alright, so first step again is you are going to look at all of the different wavelengths and try to identify at what wavelength you have a maximum absorption. And we talked about why it's important to be that maximum absorption. Because ultimately you want another graph that plots absorption at that value. So if this is X nanometers, right? So we want absorption at X nanometers versus concentration of the copper chloride solution. Alright? And as you have more and more copper chloride, you're going to see an increase in the absorption of that peak. Right? So if this was if this is the concentration of my stock solution, if I cut my solution in half, then my new concentration would be expected to be half as much, right? If I cut it in a quarter, again, I would expect it to be 25% of the original. And that's what your plot should show, because that's one of the steps you're going to do as well. Make different dilutions of your your initial stock solution, okay? And again, on your spectrophotometer, you need to change these wavelengths frequently. Every time you're looking at a different wavelength, you need to manually change it. And every time you change the wavelength, you also need to add in a blank and blank your sample. These are all things that we discussed before. Now, on these spectrophotometers over here, we have a few extra abilities, all right? And you will be able to work with these in the future if you go on in biochem or biology. And here I have an application window. I can do what's called a scan. So it is going to take all of the wavelengths between the range that I tell it to, and it's going to monitor the absorbance of all of those wavelengths. Okay? So I have this software here open, ready to go. You'll learn about how to use the software later. There's another video in this series that also talks about the software. And if you're interested in it, you can look at that a variety of times. But there's no rush in learning how to use this software at this point. But the thing I want to show you is how this spectrophotometer is the same thing as what you guys are dealing with, but it has a few different abilities, and it might help you visualize what the spectrophotometer is doing. So here we have a plot. This is wavelength along the bottom, and this is absorption along the y-axis. All right? They don't give us our values here, our labels, but if we push start, the first thing it's going to ask me for is a blank. All right? It asks us for the blank. The software does that for us. The sample or the work that you're going to be doing in the Gen Chem lab, those spectrophotometers won't remind you to put in a blank. So you have to remember every time you change the wavelength, you add a blank. So it says please insert next sample, which is, and they have identified it as the blank sample. Again, when I handle my cuvette, I want to be sure that I handle it. I'm not touching the windows here, correct? If I do touch the windows, not all is lost, right? I can get a napkin or something, maybe the inside of your lab coat or something, to polish it up, right? So that all of the fingerprints are gone, right? So again, if you want to handle this, you can handle it along these sides. Some cuvettes are clear on all four sides, right? They have different uses, different applications. These are the kinds that we're going to be using in our lab. If you use this one, that's fine, but you'll find it requires more sample. And these do provide ability to do experiments that these ones don't, so we prefer to use these kind. But that doesn't matter if you use this kind, which is just going to require more sample. But if you do use this kind, you have to identify what two sides you can touch, so that you don't accidentally touch the sides that you're going to put in the beam of the light. And again, if you do, you can always polish it with a Kleenex or something. And that's what you should probably do every time you use that one. This one here, the light goes this direction, right? From my left to right. So I put the sample in this way so that the beam will go through the long ways, the long 1 centimeter length of the cuvette, right? Again, in the lab, you are going to put your sample in this way because the light runs towards you, right? So you want the long end of the cuvette to be in that direction. All right, so I put this in because it's asking for a blank. So I put in something that's just nothing but my solvent. And if I was working with solution or solvent or solutes dissolved in ethanol or dichloromethane or some other solvent, then I would want my blank to be that solvent as well. But again, it depends on what wavelength I'm interested in. If I'm interested in something between 400 and 700 nanometers, then if it's colorless to my eye, it's a blank, right? Because if it doesn't absorb color to my eye, then it doesn't absorb between 400 and 700 nanometers. All right, so I put in my blank, I push OK, and now it scans the whole wavelength, and this kind of takes a little bit of time. But what it does is it scans from 800, 400, and checks the checking how fast I have it to go. Okay. Okay, now it's asking for my sample. So I have a few samples here. We have a yellow, a pink, and kind of a purplish color. All right, so if I put my yellow one in, again, the same way I have right to left, same as my blank. Now I push enter, and I can watch here. So it's already, it tells me that it's at 600 nanometers, so it started at 800, it's moving along that way. And it doesn't look like there's any absorbance. The absorbance value is 0 here. Now it's at 450, now it's at 400. Oh. There we go. So this was our sample that we just ran. We were on the wrong window. All right. So it's running a second scan of that same sample. So I can follow that red scan there. So we've told it to focus in on just the line itself, right? So we see that this sample, this yellow sample, has a peak right about here, right about 430, 425 nanometers. Okay. And it's running scans over and over because I've set it up that way because I'm going to change the samples every once in a while. So here, if I put in a red sample now, I added the red sample, and my red sample has a peak, a different peak, right? So this was my yellow sample, my red sample has a different peak, but you can see also there's a shoulder right there, right? So it looks like that this sample, the chemicals in there don't just absorb one wavelength of light, they have a couple of wavelengths that they absorb. And that's true for all of these samples. This does that's the maximum absorbance, but all this range in here is being absorbed by the chemicals. And again, when we talk about absorption, that means that the electrons in this sample are excited by this wavelength of light. All right? So now we'll put in our blue sample here. And you see, if you try to look through there, you can see it's dark. You can see some light, but it's very dark. So the chances that light are getting through is minimized. So we would expect a very large absorbance on a sample like this. And here you can see it going up there. It's already heading up off the top of the graph. Okay, but it didn't quite go off the top there. So we do have a very, very large value. Now, when you're dealing with absorption spectroscopy, right? And the units are absorption. If you look at the conversion between transparency and absorption, and transparency is the log of the light that comes out of your sample over the light that goes into your sample, right? So that's how you identify absorption. Absorption is the transparency, the log of the transparency, which is absorption in or absorption out over absorption in. So, using that equation, you can go back and look and you'll see that when the absorption is at 1, if the absorption usually is 1 at this value here, then that means that 90% of the light has already been absorbed by the sample. So that only 10% of the light is getting through. So from here to 2.44 here, that means that we're only dealing with a change in 10%, yet we have such a huge peak. For that reason, it's important that we focus on the region between 0 and 1 and make our samples so that they fall between 0 and 1. If we make our samples fall above 1, then we increase the probability of having error. All right? And if it's below maybe 0.1, for example, also increase the probability of having error. So, for the same reason, down in the low values, only a small fraction of light is actually been absorbed. So if we want to change that scan so that this comes down within the region of 1, right? Well, this is my original sample here. And there's a few things I can do. We talked about in recitation how if the absorption is too high, and your computer or your spectrophotometers in your lab won't even go up to 2.44. So this would definitely be going off of the charts. So you can make a dilution. So you make a dilution. I'll just use this for now. We're not being quantitative, we're just making a dilution. So I'm going to transfer a known volume of my solution, and then we're going to transfer, rinse this out really quick so we can use this as our water. Okay, so now I've diluted it with one whole volume, so the absorption should be half as much, right? So we were at 2.44, so we'd expect it to go down to about 1.2, but we see that it's not. And that's probably because 2.44 is just, it's not really actually at 2.44. The amount of light that could have been absorbed is much higher. So we have a significant amount of error there. All right, so here comes again, they're going to scan it again to see where our maximum is. So the maximum is about 1.65, okay? So we're still a little bit higher than 1, so let's dilute it again. Alright, so we have another dilution. We should have half the amount of absorbance as that previous one, which was 1.65, and this one is about 0.8. Alright, so that's pretty close to half as much, right? So we see that around 1.6, we still, if we dilute it 50%, then the value goes down to about 0.8. Alright. And we would expect the same thing if we were diluted again, another 50%, it would go down to about 0.4. Okay, so we have our pink sample here. We ran the pink sample, we ran the yellow sample, and we have the purple sample. So again, the yellow sample, where did the yellow sample go? The first one was our yellow sample, correct? Did we run the yellow sample yet? Let's try to put the yellow sample in again. What's that? So here's the yellow sample now running across. I thought we had the yellow sample on there previously. Anyways, there it is again. There's the absorption of the yellow sample. So we have our yellow color here, our pink color was here, and our purple color was in here. Alright, and again you can see the purple color has a little bit of absorption, a little shoulder there as well. So this is showing us all the wavelengths versus the absorbance, and it'd be very easy, very quick to identify that peak absorbance, right? And then, I'm going to stop here. After you identify your peak absorbance, like in your lab, then you're going to just stay right at that one absorption, right? Right at that wavelength. And you can do that here by going to a specific wavelength, maybe 400 nanometers you want to go to. And so you just say, you just change the cursor, and then it will go to 400 nanometers, and the absorption value will be right there. So then you can just put in your sample, change your sample, and you'll see that the absorption value changes, right? So then it's acting just like your spectrophotometers over there in the bio or in the general chem lab are. All right, so a little introduction to this, hopefully a little bit of a hopefully a little better understanding of what is going on here when we're changing the wavelengths to find the maximum absorbance. And when you come to this spectrophotometer, you'll also have a little bit of experience using it as well. All right.